In this video, we'll look at some circuits with both mutually induced and self-induced induction. So they will have coils that are magnetically coupled. In general, a non-zero current can flow into each of the two coils, and the mutual voltage will be present independently of and in addition to the self-induction. There we go. So if we look here, if we look at this transformer circuit, we don't have the rest of the circuit past V1 and V2, but we'll assume these currents are in fact flowing. There's something attached. We have closed circuits on each side. So our voltage V1 is going to be equal to the L1 di dt according to passive sign convention, but it's going to be plus or minus that mutual inductance times di2 dt. The plus or minus, whether it's plus or minus, depends on the dot convention at each of these two coils. And similarly at V2, we'll have the self-induced voltage across V2. This is set up according with I2 and V2 according to passive sign convention. So that'll be L2 di2 dt. The mutually induced voltage, however, again, it'll be plus or minus M di1 dt, as that depends upon the dot convention. So let's look at the two different scenarios where we have both the dots at the top or we have both the dots at the bottom of these coils. In both these scenarios, we're going to be adding the mutually induced voltage. In this scenario, passive sign convention, again, we have V1 M L di dt. That's according to passive sign convention is VL. But since we have I2 flowing into the dot, the mutually induced voltage is also positive at the same dot. So we end up with the sum of the mutually induced voltage. And similarly at V2, I1 flows into the dot, so it creates a mutually induced voltage up here at the dot, which is a positive reference of V2. If they're both of the dots are both moved to the bottom, we still have a positive. We get that V1 is still L1 di dt, that's our passive sign convention, but since I2 is flowing into the non-dotted terminal, we get the mutually induced voltage positive reference up here at the non-dotted terminal. So both these scenarios come out the same in terms of their mesh equations. These would be their mesh equations here. If we look at the scenario where we have one dot at the top and one dot at the bottom, and again we have both these currents flowing into the inductor. They're not set up according to mesh currents. Mesh currents are always clockwise, so I2 is set up here going counterclockwise. Well, now we have in each of the scenarios, we've set them up so our self-induced voltage according to passive sign convention will be positive, I1 and V1. I1 flowing into the positive voltage reference, but now I2 is flowing into the non-dotted terminal, so the positive mutually induced reference is down here at the bottom. So it's going to have a negative. We're going to end up with our L1 di1 dt minus M di2 dt. And similarly, since our I2, we end up with V2 is going to be L2 di1 dt, passive sign convention, but I1 flowing into the dot is going to create a positive reference down here at the bottom. So that positive reference at the bottom leaves a negative reference at the top, so you have minus M di1 dt. So one of the things that I find helpful is I like to draw, even though I'm looking for V2, I like to draw, okay, this is my plus or minus VM12. This is, yeah, actually that's the opposite. I did that wrong. So I drew that. I like to do it. I like to be able to erase it. So because I1's flowing into the dot, this is my plus or minus VM12. And since I2 is flowing into the non-dotted terminal, here I have a plus or minus VM21. So that helps keep track of whether you're adding or subtracting. And you can show to yourself that, the opposite references get the same scenario. So all these four scenarios that we've shown, we have positive passive sign convention, and then we could have positive or negative mutually induced voltage depending upon the dot convention. It is possible, however, that I1 and VM1 are not set up according to passive sign convention. In that case, we could have a negative L1 di1 dt. And here we turned I2 around here. So we turned I2 around so it'd be like a mesh current flowing clockwise around here. So we have I2 flowing into the non-dotted terminal. So we have the positive reference down here, and we have our plus or minus VM12. And similarly, on this side, we have our I1s flowing into the dot, so we have our plus or minus VM21. In both these scenarios, the positive reference is associated with what we're considering the positive voltage V2. However, in both these scenarios, it's negative because it's set up in terms of active sign convention, V1 and I1, V2 and I2. So that's nice to be able to use our VL is L di dt and VM is plus or minus M di other dt. But we could also do this in frequency domain. So in frequency domain, these inductors their impedance depends upon the frequency. So we can call this inductor L1. We can consider this impedance to be J omega L1 ohms instead of L1 henries. And here we have J omega L2 ohms instead of L2 henries. So then we can write our voltage equation in terms of in frequency domain. So whereas L1 and L2 have an impedance of J omega L1 and J omega L2 respectively, M, since it's also a unit of henries, has a impedance of J omega M ohms. And we can write these in terms of frequency domain equations. So this is probably what we're going to be doing, since as long as we're in sinusoidal steady state, we can use these frequency domain equations and we can use these terms for impedance. So again, these two are set up in such that our mutually induced voltage has the same positive sense. For V1 and V2, again, our mutually induced voltage over here, since I1's flowing into this terminal, we have a positive at the top. Down here, we turned around, we changed the direction of I2. So although I1 flows into the dotted terminal, it has a positive reference for up here at the top in terms of the mutually induced voltage. The self-induced voltages are both negative because they're not set up. This plus and this current are set up in terms of active sign convention. So let's look at an example here. We have a voltage source with a series resistance set up. This is really a transformer, so these two mutually induced coils, and the secondary side of the transformer, or the second coil, has also attached to it a 400 ohm load. So we want to solve for the ratio of V2 over V1, where V1 is this voltage source presented by this voltage source, and V2 is the voltage across the this 400 ohm resistor. But if we look here, this is V2 over V1, this is phasors, so we need to convert this to frequency domain in order to solve this problem. So we convert to frequency domain. We know the frequency 10 radians per second, so 1 Henry becomes J10 ohms, 9 Henry becomes J90 ohms, and 100 Henry becomes J1000 ohms, or J1 kilo ohm. So what we want to do here then is write our mesh equations. So when we go to write our mesh equations, our first mesh equation, we have I1 flowing through 1 plus J10 ohms. So we write 1 plus J10 times I1. But why do we write it like that? So there's our VR, and we'll put it on this side, this direction. There's our VL, right? So when we do that, what we have is negative V1 plus I 1 ohm I1 1 ohm plus I1 times J10. So we can just combine these, and then we put, since this was negative J10, right? If we wrote our KVL, it'd be negative V1 plus I1 times 1 ohm plus I1 times J10 ohms. But what do we do about the mutually induced voltage? So the mutually induced voltage here, we have I2 flowing into the non-dotted terminal, so it's going to create a voltage in this direction, right? That's going to be our plus or minus Vm. There's our Vm there. So since it's in the opposite direction, we came into the negative terminal. That's a minus Vm is equal to 0. And since Vm is J90 I2, that's our Mi2, that's J90, we can say this is our mesh 1 equation. So why don't you take a moment and write the mesh 2 equation. Pause the video. When you come back, we'll show the mesh 2 equation, and we'll solve these equations. So again, hopefully you got the mesh 2 equation. There was no voltage source over here. We had I2 flowing in the positive direction, what we're calling positive voltages of plus minus VL plus minus VR. That's our 400 plus J1000 I2. But if we look at that mutually induced voltage due to I1, it created the positive reference up here. So that became, when we're going in this direction, we're going into the negative terminal. So that's a minus J90 I1. So these are our two mesh equations. We want to make sure we can write these mesh equations. That's the first most important step. And then of course we can solve for them. We go and solve for them. We solve for I2 and I1. And we see that I1 is about 20 times I2, and they're a little bit out of phase. So what we had is we had a decrease in current across this transformer, these mutually coupled coils. We had 2 amps flowing in and only 1 amp induced to flow out. There's nothing else. This is only a magnetically induced current flowing over here. There's no electrical induction because there's no voltage source on this side of the coil. So we only are getting a mutually induced current. And that mutually induced current is decreased by a factor of, just approximately 20. It's less than 20. But if we look at the voltages, what's V2? V2 is I2 times 400 ohms. So our V2 has increased from V1 by about 6.8 times, approximately 6.9 times. But there's also a phase shift. Our V1 had a phase angle of 0. Our V2 our V2 right here, a phase angle of negative 16.7 degrees. So we had a voltage gain and a phase shift. So we managed to get a voltage gain across the mutually induced coil. That's this voltage is being induced by the current flowing through I1. How does the current flow through I1? It flows through I1 due to this sinusoidal voltage source. This is like a 10 cosine 10t. Right, so we're analyzing it in frequency domain. So we have a voltage gain, but we don't have a power gain. We had a voltage gain and a current loss. If we went to calculate the power, that would be the magnitude of V1, magnitude of I1, cosine the difference of the angles. That's still going to be greater. This V1, I1, the power being produced by this voltage source is greater than that being absorbed by this 400 ohm resistor. We also have this phase shift. If we have no phase shift, it is possible to get a scenario where we have no power loss. So we have an ideally mutually coupled coils. There's no power loss. All the energy from coil 1 is captured in coil 2. That's possible, but we can never have a power gain. That's impossible. So let's look at some of the boundary conditions. What if we replace this 400 ohm resistor with a short circuit? We let that be a short circuit across our second coil there. What's going to happen then? Well, then V2 has to be 0, right? The voltage across the short circuit is 0. So our V2 over V1 is equal to 0. If we replace it with an open circuit, then we just get our V2 is just j omega m I1, right? It's just the we just have the mutually coupled voltage, which is in this direction. I1 flowing into this positive terminal is creating, this is an open circuit, if that's open. So it's just our j omega m I1, and our we divide that by our V1, which is just the V1 is this it's got to be the same as this voltage, which is j omega, excuse me, is I1 times 1 plus our J10 ohms. So that's what's equal to V1. There's no mutually induced voltage because it's an open circuit. So that's the other side of our boundary condition. If we look at that scenario, we end up with a V2 over V1 on the order of 8.955 with an angle of 5.711 degrees. So those are our boundary conditions as we change this load from a short circuit to an open circuit. In that range, our ratio of V2 over V1 goes from 0 to approximately 9, but we also get this phase shift, so the phase shift will change in there. And that's just by changing this load resistor here. So that's taking a look at this, this mutually coupled circuit or magnetically coupled circuit in frequency domain. We've also taken a look at it in time domain. If we take a look at this circuit here quickly, I'd like you to try this, where here we need to write time domain equations. Can you see why we can't convert this to frequency domain? We will learn to in later modules, but right now if we look at this source, it's 20e to the negative 1000 t. That's an exponentially damped function. It's not a sinusoidal steady state function. So what we've done is we've learned to represent inductors in terms of their sinusoidal steady state impedance. That j omega L is if we have a sinusoidal forcing function. Here we don't have a sinusoidal forcing function, but we can still write our mesh equations in time domain. So why don't you pause the video for a second and write these mesh equations in time domain, and then you can check to see if you got them correct. So go ahead and do that. All right, so these mesh equations in time domain, we have for our mesh 1, we do have a voltage source. We set that equal to, we have I1 flowing into 3 ohms plus 2 milli is 0.002 Henry, di1 dt, and we negate. The big key here, so our self-induced voltage across the inductor, our mutually induced voltage across the inductor, since this dotted terminal is at the bottom, the mutually induced, mutually induced is, that's a negative, sorry about that, is in this direction, right? So there's our VM, so we end up subtracting that. If we go over here to our this mesh equation, we have I2 flowing through 5 milli and 10 ohms. So there's our I2. We have to separate that out, these two terms out, right? Because one's di1 dt and one's just I1. But again, since I1 flowed into the non-divided terminal, this is the direction of our mutually induced voltage, and the direction of our mesh current is that way. All right, so that's it for this video.